Hi everyone, my name is Quoc. I'm a researcher at Google Research. Today I will talk about some of our recent work on neuroarchitecture search and meta pseudo labels. This is John work with many people at Google. Around 2018, we looked into the state-of-the-art architectures in ImageNet classification. And as we plotted the accuracy and the number of parameters, we saw a clear trend. As the model gets bigger, the accuracy also gets better. This is a blessing because we can scale up the models and get better results. But at the same time, the curse is that the x-axis is in log, and making the model 10x bigger can only improve the accuracy just a little bit. Our thought exercise back then was that even though it's true that bigger models are better models, can we improve their efficiency? In other words, can we develop a new class of models that have better slope in terms of the relationship between accuracy and parameters? If we find a new class of models with better slope, training and inference will become a lot faster. It means that we will save a lot of compute and energy. And this is what many tech companies are really interested in because we want to deploy this model um, uh, at large scale. Uh, to achieve this goal, we adapted a neural architecture search framework to become aware of efficiency. The key idea here is that in neural architecture search, we use a controller to sample models and then train them. The accuracy and latency of the models are then uh, used to improve the controller such that the controller will prefer better accuracy and better latency model. Neural architecture search in general also needs a human design subspace. We often started with a subspace that this subspace of the very best human design models. And back then we started around the mobile nets subspace. So in this subspace, the controller is able to change the configuration of the architecture. For example, how many times you repeat a layer, and what is the kernel size, and number of filters, and the skip connectivity, etc., and etc. And searching for a good network is very expensive. So we also constrain the model to have around 5 million parameters and keep this in order to keep the search cost down. With this constraint, we find a model called efficient at B0, which has better accuracy and parameter trade-off than DenseNet and ResNet 50, for example. Here the x-axis is the number of parameters and the y-axis is the ImageNet top one accuracy. So the top left corner of this figure is what we want. In other words, we want models that go up to the top left corner of this figure. However, finding one small model that has high accuracy and latency trade-off in the small model size is not enough. We want to have uh, models that are also better in large model size as well. So, for example, can we search for a better network than the SENet? Um, so for this, instead of searching for large models, we apply model scaling to efficient at V0. We discover a method named compound scaling, which scales both the width, the depth, and the resolution of the network to balance these three aspects of scaling. So in previous work, people only scale either the width, the depth, or the resolution alone. But in this paper, we propose to scale all these three elements at the same time. So using this principle of compound scaling, um, we discover a family of models from B0 to B7 architectures. And where B1 to B7 are just scale-up versions of efficient at B0. These models are highly efficient. For example, B4 is 10x more efficient than SENet in terms of parameters, but has the same accuracy. In 2019, EfficientNet V1 achieved state-of-the-art accuracy and parameter efficiency trade-off. The frontier curve of EfficientNet is much better than human-designed models, as you can see here. However, small models may not be fast. So recently, we started looking into real latency on GPU and TPU. Following the same principles of EfficientNet, we developed a new set of models called EfficientNet V2, which achieves state-of-the-art latency and accuracy trade-off on GPU and TPU. From this figure, on GPU V100, the frontier of EfficientNet V2 is much better than other models. So a lot of people have, there's a lot of excitement around vision transformers, for example, but if you compare EfficientNet V2 and vision transformer, you can see that EfficientNet is much faster than VIT if we train on ImageNet and ImageNet 21K. So here are some of the references for neural architecture search and EfficientNet V1 and V2. We have also used NAS to search for fundamental building blocks in neural networks. Perhaps the most successful one is the search for a new activation function. Here we found the activation function x times sigma x, which tends to work well for many vision and NLP applications. This activation function was also previously discovered manually by other authors, and it's called SEAL or SILU. This activation function right now is used in many state-of-the-art networks like EfficientNet V1, V2, and also MoveNet V3. We recently combined EfficientNet with semi-supervised learning, a semi-supervised learning method called meta-pseudo labels to achieve the milestone accuracy of 90.2 top 1 ImageNet accuracy. Up until May 2021, which is very much last month, it was the state of the art and also much better than many previous networks. So how does it work? So so we started with a method called noisy student, and in noisy student we have a pre-trained teacher that we train on ImageNet, for example, and then we use it to generate pseudo label data on a much larger corpus of data, and then we train a student network on the pseudo label data. However, the student might learn from the mistakes by the teacher. So in order to avoid the confirmation bias, we inject some noise during the training process of the student so that the student can avoid learning from the mistakes by the teacher and becomes more robust. Consequently, the student will get better than the teacher. However, this method is not enough because the student can still learn the mistake by the teacher. So we recently proposed a method called meta pseudo labels. And in meta pseudo labels, we have a teacher that generate pseudo label data to the student, and then the student uh, will learn from the pseudo label data, but it also performs uh, s- some classification on label data. And then the accuracy on the label data will be presented as the reward for the teacher. So if the student performance is getting worse, then the teacher will know and then adapt to generate better pseudo label data. And if the student performance on the label data is getting better, then we basically the teacher will learn to adapt to continue to generate the pseudo label data like before. And this whole training loop is uh, um, to make sure that the teacher and the student are trained concurrently. So basically, the teacher we make one step update of the student by um, generating the pseudo label data, and the student will learn from the pseudo label data. So that's one step of updating the student. And then the second step is the updating the teacher by using the student performance on the label data as a reward. So the teacher network and the student network in this case are trained concurrently. So this method is called meta pseudo labels, and the paper appears in CVPR this year. Now, the we use this meta pseudo label method to train a large efficient net model called L2 that has around 480 million parameters on a dataset of 300 million unlabeled images, and we achieved 90.2 top one accuracy. This is around 1.6% better than the previous method. And this is a big jump on this dataset because usually, half a percent or 0.8% on this dataset is already considered very big. And these checkpoints are open source. And a lot of people told me that if you use these checkpoints to fine tune on downstream datasets like CIFAR 10, CIFAR 100, or flowers and so on, you will immediately get much better results on these datasets. And a lot of people on Kaggle also use the checkpoints here, meta pseudo label and noisy student, uh, to win competitions as well. Uh, uh, One dominant argument against semi-supervised learning and self-supervised learning methods is that they tend to work well on small data regimes. But once we have a vast amount of label data, supervised learning method becomes better than semi-supervised learning. In other words, semi-supervised learning doesn't scale very well. And this is a problem because in many real-world applications, we have an opportunity to collect more label data. Um, so our result has shown that semi-supervised learning can work well on high data regime too, which is to many people a big surprise and represent something really magical. And this is captured in this blog post by Vincent Van Hoek around the quiet semi-supervised revolution. Um, many people are very excited about vision transformers. And around June 2021, there's this very exciting result that surpassed our result and achieved state-of-the-art accuracy of 90.45% on ImageNet. Um, This model, to contextualize this result, this model was trained on 3 billion label images and 2 billion parameters. So these are big label datasets and big models. Now, just to compare, a meta pseudo label achieved 90.2% top one accuracy. That is about 0.2% worse in accuracy. However, in terms of label data, we use 1.4 million label images uh, and 300 million unlabeled images. So in terms of label images efficiency, that is around 200 times more efficient in terms of label images. Now, you can argue that the 3 billion label images might have some noisy data, but the facts, the factor of efficiency here is about 200 also, which is very remarkable. And so, in other words, if you have an application where you cannot collect 3 billion label images, I think some semi-supervised learning method is still very suitable for you. In terms of model size, efficient at L2 is also much smaller than vision transformers. For example, our network is only 500 million parameters. So that is 4 times smaller than the large vision transformer network. So please check out some of these papers if you want to learn more about meta pseudo labels, noisy student, and data augmentation. So, for example, the meta pseudo labels paper appears at CVPR 2021. So, in summary, in this talk, I presented 2 main topics. So the first topic, I discussed neural architecture search. I presented evidence that neural architecture search can find better accuracy and latency trade-off. So for example, efficient at V1 and efficient at V2. Another model that used a lot at Google, but was found by neural architecture search is MobileNet V3. Which follows the same idea. And MobileNet V3 is also used a lot in a lot of mobile applications at Google. Neural architecture search is also used, to find efficient models for inference at Google and Waymo and cloud, etc. Quite successfully. Because efficiency, if you want to have a model that launch in a new that is deployed in a real world application, it's not only accuracy that matters, but latency is something that people care a lot about. So in the second topic, I presented meta pseudo labels, and unlike many previous works which basically advocated semi-supervised learning in low data regime, in this talk I showed that this method also works very well on high data regime. So in particular, our method achieves a milestone accuracy of 90.2% top one accuracy on ImageNet. This is the first time that someone can show that you can surpass the boundary of 90% accuracy on top one ImageNet. So with that, I can stop my talk and welcome questions.